Hello friends, our next topic is properties of matched filter. In our last video lecture, we have talked about optimum matched filter that is used to detect the baseband transmitted signal at the receiver side. Matched filter is basically a linear time invariant filter, that is LTI filter. This filter is matched to a known finite energy signal GT that is defined within interval t greater or equals to 0, less than or equals to capital T, and having an optimum impulse response that is denoted by k times of g function of capital T minus small t. This optimum impulse response indicates the time reverse and delayed version of input signal GT, that is a pulse signal. So optimum impulse response h function of t is equals to k times of g function of capital T minus small t, that is in time domain. And in frequency domain, it is given by capital H function of f equals to k times of g star f e to power minus j 2 pi f capital T. Here g star f is the complex conjugate of g function of f. Now for the discussion of the properties of matched filter, we use optimum impulse response. So we move to the properties of matched filter, and according to this, the peak pulse signal to noise ratio or maximized signal to noise ratio of the matched filter depends only on the ratio of the signal energy to the power spectral density of the white noise that is at the input side of the filter. So here we derive peak pulse signal to noise ratio that is equals to the ratio of signal energy upon power spectral density of the white noise. For this, we take frequency domain representation of matched filter having g function of f as input signal, and output of this matched filter is g naught function of f, that is equals to product of h function of f into gf, that is in frequency domain. In place of h function f, that is the optimum impulse response of matched filter, we can write k times of g star f e to power minus j 2 pi f capital T. And we know that g function of f is the complex conjugate function, and the product of any complex function with its complex conjugate is equals to square of the mod of that complex function. So g naught f, that is the output of the matched filter, is equals to k mod square of g function of f e to power minus j 2 pi f capital T. Now, in order to determine output in time domain, we take inverse Fourier transform at t equals to capital T. And it is given by g naught function of capital T equals to integration g naught f e to power j 2 pi f capital T into df. Now, in place of g naught f, we can write k mod of gf square into e to power minus j 2 pi f capital T. Now, the exponent term are cancelled with each other and we get g naught function of capital T equals to k integration mod of gf square into df, taking limit f equals to minus infinity to infinity. And here integration of gf square into df is nothing but the energy of the pulse signal gt, that is denoted by capital E. And the output in time domain g naught function of capital T is equals to k times of capital E, that is the energy of the power signal. And here in our discussion, we have to determine peak pulse signal to noise ratio. For this, we take numerator mod of g naught function of t, that is capital T whole square. And according to this, mod of g naught function of capital T square is equals to ke whole square. That is equation number 1. Now we again use matched filter that is correspond to the noise. Here at the input side there is a Gaussian white noise denoted by W function of T, and its power spectral density is N0 by 2. Here N0 is the average noise power per unit bandwidth. At the output of the match filter, we have filtered noise denoted by N function T, and its power spectral density is denoted by Sn function of F, and it is equals to N0 by 2 times square of the magnitude of impulse response of matched filter. So the power spectral density of filtered noise is equals to N0 by 2 H optimum F mod square. Now, the average power of output noise Nt is defined by expectation operator, that is denoted by capital E n square function of t, that is equals to integration of Sn function of f into df, taking limit f equals to minus infinity to infinity. Now, in place of Snf, that is the power spectral density of filtered noise, we can write N0 by 2 mod hf square, that is optimum impulse response. And again, in place of h optimum f, we can write k g star function of f e to power minus g2 pi f capital T. And the mod square of this optimum impulse response is equals to k square mod gf square into df. Since g function of f is a complex function and mod of g star f square is equals to gf mod square, and we know that the mod of e to power minus g2 pi ft is equals to 1. So we get expectation of n square t equals to k square n0 by 2 integration gf mod square into df. And here integration of gf mod square df is nothing but the energy of pulse signal gt, that is denoted by capital E. So the average power of output noise, that is denoted by expectation of n square t equals to k square n0 by 2 into E, that is denoted by second equation. Now, in our discussion, we have to determine the peak pulse signal to noise ratio, that is sampled at t equals to capital T. So we take ratio, that is eta max, and the ratio is mod of g naught function of capital T square upon expectation of n square t. In place of g naught function of capital T mod square, we can write k e whole square, that represents the energy of the signal, and at the denominator expectation of n square t is equals to k square n0 by 2 into E, that represents the average power of output noise Nt. So after rearrange or cancellation, we get eta max equals to 2 into E upon n0, which is the ratio of signal energy denoted by capital E to the noise power spectral density n0. And according to this discussion, we conclude that using matched filter, the maximized signal to noise ratio is totally independent of the input signal Gt. That is the important property of using matched filter. Here we note a point. The operation of the match filter is called spectral phase matching because in the operation, the match filter brings all the frequency component into the same phase at t equals to capital T. So the match filter operation is called spectral phase matching. During this spectral phase matching, the amplitude of the output become maximum. And this peak value of output signal at t equals to capital T gives the optimum output signal to noise ratio. And this optimum output signal to noise ratio is used for the optimum detection of baseband transmitted signal. So accordingly, The property of the matched filter is the optimum detection of baseband transmitted signal, and for this we take peak pulse signal to noise ratio. And this peak pulse signal to noise ratio is simply the ratio of signal energy upon power spectral density of white noise at the filter input.